Thank you very much.
Okay.
Okay, welcome back to everybody online. Welcome back to Stephen's second lecture. So, Stephen, thank you.
Thank you. Since we're off time a little bit, someone just remind me when we're stopping. Don't let me go forever. Okay, I guess we went over an hour without me giving a single example somehow. So just recall so far how I've defined a moment angle manifold as something associated to a simple polytope P. And this was like just an M torus if M is the number of facets that P has, across P itself, which is some n-dimensional thing, modulo some way of quotienting coordinate subtori over certain points of P. So just to give a quick example, which we'll come back to in a moment with a different definition, it's like a very small, simple polytope, namely just the interval. So here, n is 1, m, number of facets would be 2, right? Our codimension 1 faces here are really just the vertices, or I should call this like facet 1 and facet 2. And then our definition is just saying a moment angle manifold will be a 2 torus across an interval, modulo some equivalence relation. And the way this looks is like, okay, 2 torus, just S1 cross S1, across an interval. And we said over the like actual interior of a polytope, there's no quotienting going on. And over certain codimensional faces, we have some quotienting. So like over this facet, we will just quotient out a coordinate circle on the one end of the torus. And over this point, we'll quotient out, we'll collapse the other coordinate circle, right? So this just becomes like x, y0 is related to any x prime, y 0. And at the other end, xy1 is related to any x, y prime 1. So that is otherwise known as the join of S1 with S1. Which is the same thing as the suspension of the smash. So we get S3 as our first example of a moment angle manifold. So I'll remember to come back to this definition, or sorry, this example in a moment after we see the more modern definition. So I'll now start telling you how Bukstauber and Panov reimagined these definitions using polyhedral products. So now the combinatorial input will change a little bit, become more general. So recall abstract simplicial complex K on the vertex set M, which I'll always just write like this. It's just like a set of sets, okay? Subset, it's power set, which is like downward closed, right? So I'll call the elements of K faces or simplices. If sigma is a face of K and like tau, subset of sigma, then tau should be a face of K as well. So, here's a simplicial complex thought of as a set. This is just like a facet. This is vertex 1, 2, 3, 4. 1, 2, 3. That's like a maximal face. So that and all of its subsets, 1, 2, and all of its subsets. And the empty set will always be a face. So I'll always assume K contains the empty set, and all the vertices, like all the singleton vertices, I'll consider faces. Thank you. Yes, I did. Yeah, so notice it's enough to specify the maximal faces. And similarly, this will come up later when we talk about Stanley-Reisner rings, K is also completely determined by like the minimal non-faces. So here, minimal non-faces, sometimes called the missing faces. I'll write that set as MFK. So what would that be here? I think we only have 2 missing faces, really. Sorry? Well, 1 isn't a missing face, like 1 on its own. Each vertex on its own is a face, but like 1, 3 is missing. That's a minimal non-face. And 1, 4 is similarly missing. And I think that's it, right? So like 1, 2, 3 is a missing face, but it's not minimal because 1, 3 is missing. So if you just knew this, that also completely specifies your simplicial complex. One, 2, 3, 4 is also a missing face here, but it's not a minimal missing face because it contains like 1, 3 and 1, 4. A minimal non-face is just a non-face of K, all of whose proper subsets are faces. So if I did include this 2 cell here, 2, 3, 4 would certainly be a minimal non-face because all of these properties, these edges are there. Okay, so yeah, like I said, this will come up later. This allows you to go sort of back and forth between simplicial complexes and certain square-free monomial ideals. The singletons I will always consider faces. Sorry, what was the question? Yes, for me, or in these talks, yes. They're sometimes called ghost vertices. Maybe 1 or 2 places, constructions where it comes up where you might want to like start with simplicial complex and restrict to other vertices. And yeah, but for the most part, I'll assume K does not have ghost vertices. Okay, so now the modern definition, starting with the definition of a moment angle complex. So this is following Buchstaber Panoff. The most important thing is a moment angle manifold, and then there are 2 sort of auxiliary definitions I went over very quickly before. So now we're going to associate a moment angle complex to any simplicial complex. This word complex is going to be sort of overused, but in this term, it's referring to like a CW complex, not a combinatorial object like a simplicial complex. Associated to K is, okay, maybe I should specify it's thought of as a space. It's usually written with this like script Z. I don't know if I'll keep that up or not, but so we're going to take the union over all faces of K of certain M-fold products of circles and disks. For every face sigma, consider the space D of sigma, which is just an M-fold product of yi's. Where each yi is either a disk if vertex I is contained in sigma, or the circle if I is not in sigma. So I'm always going to think of the disk in this way. S1 are complex numbers of length exactly 1. And by a torus, TM will always mean this compact torus, an M-fold product. Thank you. Okay. So notice D is just a simple diagram, right? We can think of a simplicial complex as a category in the usual way. Simplicial complex is a poset. This diagram is just associating every element of K a product of disks and circles. Okay, so yeah, this is also just all those M tuples of complex numbers where the only restriction is that the ith coordinate should lie on the boundary of its disk when I is not in sigma. And this agrees with the homotopy colimit of this diagram. Notice that since sigma being a subset of tau implies D of sigma as a subspace of D of tau, it suffices just to take the union over like the maximal faces of K. But sometimes it's useful to remember the entire coproduct, since once you start taking algebraic invariance of the spaces, it might turn a colimit of spaces into like a colimit of groups or a homotopy colimit of algebraic objects or something. Okay, so ZK comes with a coordinate-wise action of the torus, just like before. Since this definition just puts ZK as a subset of this polydisk. Right, so if you take an M-fold product of disks, then the M torus acts on that just by coordinate-wise multiplication, rotating disks. And it's easy to see that that action restricts to this subspace. Okay, so now the moment angle complex sort of comes to us as a CW complex. The Davis-Januszkiewicz space before was defined as the homotopy quotient or Borel construction of some torus action. But Bjerkström-Panov say the Davis-Januszkiewicz space of K is defined very similarly. So dj of K be the exact same kind of colimit. But now each yi, each factor of these M-fold products is going to be a copy of CP infinity when I is in sigma, or just a point, the base point of CP infinity. I is not in sigma. Okay, these are examples of polyhedral products. You can probably imagine how you could generalize this by replacing a pair of spaces D2 in its boundary or CP infinity in its base point by just any pair of spaces. And these two are related by this torus action. Okay, so theorem. Panov. By definition, djk here, just as zk is a subspace of this polydisk. This is just a subspace of an m-fold product of CP infinities, right? And because CP infinity is BS1, m-fold product of them is the classifying space B of a torus. So let me say it this way, the inclusion of djk into CP infinity to the m, or the classifying space of the M torus, factors as follows. So you've got inclusion at the Borel construction or homotopy orbit space of this M torus action on ZK. So in particular, if you took the homotopy fiber of this inclusion, it would agree with the homotopy fiber of this map, which is a projection. Right? This bottom row is usually called the Borel fibration associated with this M torus action. So this gives us that the moment angle complex is just the homotopy fiber of this natural inclusion. So the top row is giving us like a polyhedral product model of this Borel fibration. And this fibration here, or homotopy fibration anyway, is a very fundamental object in toric topology, which is just functorially associated to any simplicial complex K. We'll call this the fundamental fibration. So we'd like to understand this fibration and all of these spaces showing up here for any simplicial complex K. Okay, maybe I'll just quickly list some properties. For one thing, it's not clear how this relates to the previous definition yet, which was just giving us a manifold, right? I called it a moment angle manifold before when we were associating things to a simple polytope. So here, if K happens to be a sphere triangulation, say its geometric realization is an n-1 sphere with m vertices. And this moment angle complex turns out to be a manifold. Dimension m plus n. And it's known to be smooth if K is coming from a simple polytope, namely if K is the nerve complex or like the boundary of the dual of P. So notice we can associate a simplicial complex to any simple polytope by first taking the dual simple polytope. Remember that gives us a simplicial polytope. And the boundary of a simplicial polytope is a simplicial complex by definition of a simple polytope, or sorry, simplicial polytope. So there are a lot more sphere triangulations than there are polytopes, but the ones that come from polytopes will give us a smooth manifold, and those recover exactly Davis and Januszkiewicz's definition. So in this case, it can be shown that this recovers the previous definition. Okay, maybe I should be a bit more precise about that.
You wanted to have the same number of vertices as it has facets? Yes.
So we're starting with a simplicial complex now. So facets just mean maximal faces. So no assumption on the number of facets in general. We just any simplicial complex gives us a space called the moment angle complex. But if K is the boundary of a simple polytope with m facets, n here, notice, would be the dimension of the polytope since the boundary is n-1 sphere. So let me be a bit more precise about that. I'm saying K being the boundary of a simplicial polytope implies there's actually a TM equivariant homeomorphism. Between this moment angle complex and what I was calling ZP before.
Mhm.
So yeah, P here would have m facets and dimension.
I still don't get why K then has m vertices.
I think what he's asking is that the number of vertices of K is the number of facets of P.
Yeah, so
Does that
if
answer your
P,
question?
if P is an n-dimensional polytope with m facets as it was before, then its dual is a simplicial polytope where like the facets and vertices sort of switch roles. Yeah. So m facets means that its dual has m vertices.
You start with the vertices and you make a simplex if they span a face.
Yeah, that's why this is also called the nerve complex, right? Just label your facets 1 through m and call a subset of them a face of K if they're like all intersecting.
Yeah, so this might already be in your like list of properties, but in case you don't get there, I'll ask while we're doing it. So if I have like two homotopy equivalent simplicial complexes, like K or two, yeah, like how does my ZK change?
We'll see in a moment. This
Okay,
is a
it's
great
in your
question.
list.
It turns out ZK or ZK will depend very finely on the combinatorics of K. It is not a homotopy invariant of the geometric realization of K.
Okay, is it a simple homotopy invariant?
Well, notice like I can triangulate a sphere with like as many vertices as I like, right? So that's going to change apparently the dimension of the manifold I get. So yeah, I'm certainly not going to get homotopy equivalent moment angle complexes and two Ks are somehow homotopy related. Okay, good question. I'll give some examples later that'll make that a bit more clear.
I had a question.
Yeah, go ahead.
Yeah, so do you know an example of a triangulation of a sphere which cannot be realized as the boundary of a dual of a polytope?
Yeah. Hi, Kumar, by the way. There's lots of examples. In dimension 3 or less, every sphere triangulation is polytopal. 3 or less? Sorry, I think 2 or less, every sphere triangulation is polytopal. And then in dimension 3 is the first place you start to see spheres that cannot be realized as like the boundary complex of a simplicial polytope. The smallest example has 7 vertices. It's called the Barnett sphere. So this is not at all obvious. But yes, there exist lots and lots of sphere triangulations which don't come from polytopes. And it's a theorem of, sorry, I'll review this and come back to you. But there are theorems out there that say that like the sphere triangulations which are polytopal, almost none of them are polytopal in high dimensions. there's a limit, at least when the number of vertices get very big, the number of non-polytopic ones completely overwhelm the number of polytopic ones. So theorems out there that say like some limit goes to 0 as the number of vertices gets big, but you have to be in dimension 3 or higher here.
Yeah. Okay, thank you.
Gil-Kalai, that's who this theorem is due to. Okay, maybe that'll come up later as well. Okay, maybe I'll just give one other property relating to quasi-toric manifolds. That was like the third definition we had before, or very rough definition. Okay, so every quasi-toric manifold M2N, we're not going to be working too much with these, but just remember they're even dimensional manifolds with nice half-dimensional torus actions with the property that their orbit space can be identified with a polytope. That's essentially it. And these all occur as quotients, as we said before, by freely acting subtori. As follows. So consider this fundamental fibration we have, and I'm going to write it like this. ZK maps to its Davis-Januszkiewicz space with fiber just a torus, right? If I pulled this back one step, I get TM. So this is like a principal torus fibration classified by this map, which is just an inclusion. So there's our fundamental fibration. And if I can find in this big torus an M minus N subtorus such that the restriction is a free action, then I could quotient by that. And I'd have like a residual torus action over here, M minus N. It's an N torus. That would give me a fibration like this. So it turns out that every quasi-toric manifold sits in a diagram like this. And motto here, maybe, we're calling that this is our fundamental fibration over there. The actual quotient of this action is a polytope. But remember, this isn't an actual quotient, it's like a homotopy quotient. So you do the same thing over here to get this diagram. So this map, which we get functorially from any simplicial complex, factors through every toric manifold. And this residual action that we got when we quotiented out by the subtorus to get an N torus, that's exactly the like half-dimensional torus action in the case of like a toric variety, for example.
The map down, that map, what is that?
That's like the Borel quotient or Borel construction of this action. So this whole diagram extends further, right? Like this fundamental fibration really started there. So you can think of a choice of a nice subtorus that acts freely is giving you like a group homomorphism whose classifying map gives you a map from BTM to BTN. And we could just take homotopy fibers starting with this map. Okay, so example. Let's take K to be the boundary of a one simplex. In other words, K is just two discrete points. labeled 1 and 2. Our definition here is still up. So it's the moment angle complex in this case. Okay, I only have 2 faces in K, the singleton 1, the singleton 2. So I'm going to get a union of 2 things. Each of them will just be an m-fold product. So in this case, just a 2-fold product. The one associated to this face, well, this face contains vertex 1, but it does not contain vertex 2. So in the first coordinate, I'm supposed to put a D2. And in the second coordinate, I'm supposed to put an S1. And then the second piece, the big union, is the one associated to the face 2. Okay, that contains vertex 2, but not vertex 1. So I'm supposed to put an S1 in the first coordinate, disk in the second. So notice I have like a Leibniz sort of rule. This is the boundary of D2 cross D2. Which is homeomorphic to the boundary of a 4-dimensional disk. So in like the very simplest possible simplicial complex, we're getting an interesting space, S3. And let's go further. Aside from just the space, we have like a whole fibration. So in this case, DJK is just going to be like a wedge. If you look at this definition. Right, this one would just be similarly CP infinity cross a point, union a point cross CP infinity, which I think of as the definition of a wedge, thought of as a subspace of a Cartesian product. And our fibration, remember this map is just the inclusion. So that's just the inclusion of this wedge into the product of CP infinities. Yes.
The union is as subsets of T2 cross D2. Union as subsets of D2 cross D2. So that makes it a union of S1.
Yeah, this union would be over S1 cross S1, so a point cross point. So fibration star in this case recovers something called Guinea's fibration. Which sees the 3-sphere, the homotopy fiber, this inclusion.
It's not an obvious vibration.
No, not really.
Not an obvious vibration.
Yeah, 2 very big spaces in a sense. Pushing something nice and small.
Sorry, Stephen.
Yeah.
If I start with a quasi-toric manifold and I want to see it go up. Go back to this factorization through quasi-toric manifold. What's the relationship between the quasi-toric manifold and the simplicial complex? Is the simplicial complex still going to be the nerve complex of the polytope that was involved in the definition of the quasi-toric?
Yeah, exactly.
Manifold,
So
okay.
here, quasi-toric manifolds are really only coming up in like the polytopal case. So in all of this picture, we should be thinking K as being of this form. Although there are lots of other what are called like partial quotients of moment angle complexes, which aren't like a maximal freely acting subtorus. You can take all kinds of subtori here or other subgroups and get all kinds of interesting spaces. And just in the exact same way, their homotopy groups, for example, are completely governed by this one space, right? Because they'd sit in some fibration this way.
Thank you.
Yeah, thank you. So K here, everywhere could be written as P.
So in the case of S3, it's not.
This might be a very stupid question, but in that case, in the example,
you're saying like why when to determine why I, so you're saying I belongs to the sigma or does not belong to sigma. What is sigma actually?
The little sigmas are the faces of K. So the union is over just all faces of K in
Okay.
general. And a simplicial complex we just think of as like a set of sets, right? I mean, usually we think of a simplicial complex maybe as a picture like this,
Yes.
but the faces are just the sets. So they're sigma, tau, these will always just be some subsets of my vertex set that I write like that.
Okay.
That's why you get a diagram.
Okay. Okay. Yeah, now it makes sense.
Thanks, yeah,
Thank you.
okay.
Thank you for that question. Questions, please?
Any questions online, please? Thanks, Stephen.
So going back to Martin's question about quasi-toric manifolds, what they have to do with K, maybe we should stick with this example for a moment and think, okay, to get a quasi-toric manifold over this K, over P, the P here I guess would just be the interval, right? This is the boundary of the dual of that polytope. So from Bierkstauber-Panoff's point of view, this is how quasi-toric manifolds arise. Can we think of any freely acting subtorus of the two torus that acts on this ZK? So ZK comes to us as a subspace of D2 cross D2. So it has an action of T2 cross T2. Is there a subtorus of that two torus that might act freely? It turns out the two like coordinate S1 actions do not act freely.
Yes.
The diagonal S1. Thank you very much. So yeah, in this example, notice M was 2, the number of vertices. N was 1. So we're asking, are there any n minus n or 1 dimensional subtori? So the S1 cross S1 action on D2 cross D2 here restricts to an action on ZK. And Martin is suggesting this diagonal M minus N dimensional torus. And here you can check that this really does act freely. And the quotient is going to give us a toric variety, actually. The only sort of obvious toric variety over an interval as your polytope, namely CP1. So thinking of that as S2, and our horizontal fibration here is exactly the hop fibration.
The beauty of that is you can actually see the hot fibration. Once you go to D2 cross D2, you can draw a picture of that fibration.
Okay, so that's a good start. Already with the really small simplicial complex, we're getting like nice manifolds like S3 as our moment angled manifold, S2 as a first example of a quasi-toric manifold, and eta, the first interesting element in the homotopy groups of spheres showing up. Okay, so I'm tempted to say more here, but as an exercise, you can check. In fact, every odd dimensional sphere is moment angle complex. So try doing the exact same example, maybe where you take K to be the boundary of delta n now, boundary of an n simplex. Notice that when K is just like the n simplex, its maximal facet is just the face 1 through m, the whole set. So the definition of the moment angle complex there would just be d2 cross d2 cross d2 m times. So you just get a contractible space. But if you take K to be the boundary of any simplex, you're going to get a sphere, the right dimension, S2n plus 1. So this exact same computation should go through there, as you can check. And in this case, our fundamental fibration is also something sort of familiar. This is like a special case of a theorem due to Porter. It's a very classical unstable homotopy theory that says there's a fibration like this. If you take what's called the fat wedge of a bunch of spaces, x1 through xm, and you include that into the product, the Cartesian product, this fat wedge. The definition is just the set of all like m tuples where at least one of the vertices has to be the base point. So when m equals 2, that agrees with just the ordinary wedge. So xi is a point, at least one I. And Porter showed that the homotopy fiber of that inclusion is a certain join, namely the join of the loops on all of these spaces. Which could also be thought of, remember, since the join is like the suspension of the smash, we iterate that m times, I guess we'll get like m minus first suspension of this smash product. So the definition of the Davis-Januszkiewicz space here is going to be like a fat wedge of CP infinities, because the boundary of a simplex, its maximal faces are just all the subsets of the vertex set except a single vertex, right? Every proper subset is a face here. So your union is looking like a union of a bunch of m-fold products of just CP infinity cross CP infinity cross CP infinity, blah, 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 with a point stuck in a single coordinate. Okay, let me just state some other examples without going through any computations to illustrate how these spaces are not really homotopy invariants of K in a certain sense. Let's stick with like sphere triangulation. So triangulations of the one sphere are easy to classify. They're all just boundaries of polygons. So from an exercise over there, this one should give us the 5 sphere. Take the boundary of a square versus homotopy equivalent geometric realization, but the moment angle manifold looks very different. So this one is also a fun exercise to check by hand. But already beyond that, working things out by hand in the way that we did over there gets extremely complicated. Here's the boundary of a polygon. Sorry, a pentagon, I mean. So K here looks like a connected sum, a five-fold connected sum, S3 across S4. Okay, so that one is not at all obvious. You're getting quite interesting manifolds, but the only thing that is clear here is that the dimension is going up as M is going up as it should, but not much else is clear. So turns out there is some pattern here. This is one of the very few families of sphere triangulations for which we know the homotopy type of the moment angle manifold. Instead of giving you the pattern, I'm going to show you a simplification. So a simplification. You could consider real analogs of all of these spaces we've defined so far. So there's something called the real moment angle complex, denoted like this, the real Davis-Januszkiewicz space, and they're defined exactly as before. By replacing the roles of D2S1 or CP infinity comma a point with D1 S naught and RP infinity comma a point. So this real moment angle complex defined exactly as before, but it's now going to be some subcomplex of an M-fold product of D1s. So it's just some subcomplex of the M cube. And the real Januszkiewicz space will be some subspace of RP infinity to the M, which is like the classifying space of Z mod 2 to the M. And another way you can think of this is as the C2 fixed points of a certain complex conjugation action. So you could think of the ordinary moment angle complex with a C2 action given by reflection in the complex plane. Right, so before we had like an M-fold product of circles in the complex plane. Here was the number, complex number 1. The fixed points of complex conjugation is just going to give us all these intervals as the fixed points. RZK, if you follow the definition, turns out to be the exact same thing, a polyhedral product associated to the 1 disks and their boundaries. Okay, so the theorem here corresponding to this family of examples goes back to Coxeter. Using some different language, he was looking at exactly these spaces, and he showed K, the boundary of an M-gon. This real moment angle complex R set K gives you some surface-oriented surface of genus G equals 1 plus m minus 4, I think, times 2 to the m minus 3. So you can check, looking at these first 3 examples of m-gons, starting when m is like 3 here. That we get the right genus. So it agrees with genera above. I think. I don't know, maybe I should start here, right? So what happens when you, I mean, this is sort of a much easier computation, right? Because once you convince yourself that these are giving you surfaces, closed-oriented surfaces, then it's just a matter of computing homology or something, an Euler characteristic check. For moment angle complexes, there's more than just the genus meaning the number of summons in a connected sum, since a surface is just like S1 cross S1. So there's a lot of interesting combinatorics here in working out the genus and also the dimensions of spheres that come up and how many of each.
It is good for 3 too.
I think you're saying that with 3, it's
yeah,
all
that's
good.
S3. Oh, sorry, S2. So it still works.
Yeah, thank you. Yeah, genus 0 in the first case.
So that's Coxeter's piano out there.
Right, yeah.
Want to check it out. See what its genus is.
Okay, remember to stop me. I've completely lost track of when we started.
Well, multiply that with too much.
Okay, maybe I'll finish with the definition of a polyhedral product that generalizes all of these examples. And tomorrow we'll get into the cohomology of these spaces and some stable splittings. So again, K, simplicial complex on the vertex set M. And let's let X underlined A underlined denote just an M tuple of pairs of spaces. They don't all have to be the same. So I'm going to write like xi, comma ai for I1 through M, as many pairs as we have vertices of our simplicial complex. A sequence of like CW pairs. I'd like them to be pointed. And with these ingredients, we can define a polyhedral product. I don't know if we say the polyhedral product of XA and K or whatever, but the associated polyhedral product, you can probably guess. It's going to be denoted XA upper K, sort of generalizing the idea of just raising a space to the mth power and taking the mth Cartesian product. So again, a colimit or a union over all faces of K. I'm going to change notation for my diagram here. XA to the sigma instead of XA to the K. But just as before, this is just going to be a way of letting our simplicial complex carve out subspace of like the m-fold product of the x's. Where this notation just means a diagram defined exactly as before. So where x bar, a bar to the sigma is a product of, I guess I was writing yi's. Which are defined as either xi or ai, depending on whether I is in that simplex sigma or not. Okay, so finally, here's the main definition. And I don't know what should get into the rest of today, but notation, all the examples we've seen so far, all the xi's have been the common space, and same with ai. So if like xi is just some space x, ai some space a, all vertices, then let's just write xa to the k. So in toric topology, we can now just concisely define spaces like this. K's everywhere, thank you. Horrible notation? Okay, I should mention then that in some of the references I listed before, BBCG would call the general thing always with some z, or two pairs of brackets, right? Like z, k, semicolon, x, a. So here's some alternate notation you might see around. Do I have that right? Sure, yeah. Too many brackets for me, though. And should just maybe say something about the functoriality in this definition. So I think unlike the first definitions we quickly went over, functoriality both in like the pairs of spaces and in K are a bit more clear now. Not going to write it all out because you can guess how this works, but of course, if you have a sequence of like maps of pairs of CW complexes or morphisms of simplicial complexes, which I'll always just think of as inclusions, only inclusions. So we can see this already in our fibration from the Melman-Angle complex to the Davies-Januszkiewicz space to BTM. This first map is just the map induced by a certain map of pairs, namely, this is again something you would just guess if you stared at it long enough, but if we took D2S1, the defining pair for the moment angular complex, and we just pinch the boundary to a point, it gives us a map to S2, comma, a point. And then we could include S2 as the bottom cell of CP infinity. As a CW complex, CP infinity has a single cell in every even dimension. So this is just including the bottom cell, or if you prefer, think of S2 CP1, and this is just the inclusion of CP1. So this map is induced by a map of pairs, and the second map can be thought of as a map coming from a map of simplicial complexes, because for any k, we can always include k and vertex set M into like the full simplex on M vertices. And the corresponding Davis-Janiszkiewicz space would just be a product of CP infinities, which we've already said is exactly this. Delta M minus 1, I guess. Or we could think of this as also being induced by a map of pairs, where you take the pair CP infinity comma a point, and you include that into the pair CP infinity comma itself. Right, that would also induce the inclusion into BTM, I suppose.
Unless K is a simplex, unless K is a simplex.
Well, if K is a simplex, this is just already BTM, and that becomes the identity just as that is. Yeah, so everything is as functorial as you could hope. In particular, if you take any subset of your vertex set, and considered like the full subcomplex or induced subcomplex, same thing as like an induced subgraph when you restrict to some set of vertices, that's going to induce some map of polyhedral products. The same is true just for any subcomplex, including into K. But if your subcomplex is full or induced, then exercise, you can show that this induced map has a retract. So this is going to be a very useful property for analyzing the homotopy types of these spaces. So show that like X A to the Ki retracts off X A to the K. Right, so we already have a map that way coming from functoriality. And in the other direction, maybe think of the bigger Cartesian products that each of these things sit in. And then just think of projecting this Cartesian product of a bunch of xi's to the corresponding Cartesian product of the xi's associated to these coordinates in big I. Yeah, pointed spaces. Yeah, I guess so. And then this is also maybe a good place to pause and think about what this vibration tells us right away about some homotopy properties of ZK. Were we supposed to stop at 5 or 5:30? Then this is a good place to stop. Thank you very much.